The last section of chapter 12 is an interesting sort of thing, and that introduces the idea of stress and strain. So you've got an object right here, and you're trying to pull on it. Now, if you think about what's happening on the inside, it's made up of atoms and molecules. Okay, I'm not going to draw all of them, so just atoms and molecules, and they all have forces between them. Okay, holding them into position. So if you pull on the molecules on this end, you're going to pull them slightly out of position. That means the forces of the other molecules pull back, but for every force equal an opposite force, so that pulls on these molecules, pulling them out of position, which means the other molecules pull back, and so you're pulling and stretching all along. That's the idea of tension, but the end effect is all the molecules end up being pulled apart slightly. And so your original object that was some length L naught is now some length L naught plus delta L. So we've changed the length by some delta L. And so now the question we ask is, if we have an object here and we're changing the length of it by some delta L, how much of a delta L really matters? So if I change the length, if delta L is 1 centimeter, if I've changed the length by 1 centimeter, is that a lot or is it a little? Well, that depends. If the original L naught, were 25 meters, and I change it to 25.01 meters, is that very much change? And the answer is no, that's not much stretching there. That's very little comparatively stretching. But if L naught were originally 3 centimeters, and I stretch it to 4 centimeters, percentage-wise, that's enormous. Okay. And in fact, if I stretch it by that much, then you can imagine I'm doing physical damage to the object. If I stretch it by this little percentage, then if you let go, it typically goes back the way that it was. And so what we do is we define something called strain. And the strain is defined to be delta L over L naught. So the strain is going to be how much that we've actually shifted it or distorted it compared to what originally it was. Okay. Now, in order to strain it, though, we had to exert a force on it. Okay. Now, what if I had two objects and I want to strain them by the same amount? I would have to exert the same force on both of them, so the total force would be double, right? Well, what if it was like one object but was twice the area? So I made it a bigger object. Well, that would be the same. It would be as if I had two objects there. And so it would take twice the force to get the same strain. And so what remains constant in here is the quantity F over A. And so we call that stress. So F over A is the stress. Okay. Now stress is obviously related to strain. So there's a relationship between the two. So we would say that stress is proportionate to strain. More stress means more strain. The proportionality we call a modulus. And so the modulus is the proportionality. Now, the modulus here for stretching is different than modulus for bending, because you can also bend something. Okay, but if we're talking about stretching, okay, then if you're going to stretch something, then the modulus is called the Young's modulus. And so we would say the stress, F over A, is the Young's modulus times the strain, delta L over L naught. Okay, now that's how a lot of books write it. Other books use a different symbol for the Young's modulus. Your textbook, for example, uses E for the Young's modulus. And E is sometimes used for a modulus of elasticity. Okay. And so different books use a different symbol there, but these two equations are identical. Okay, the Young's modulus is sometimes going to be Y for Young's modulus, and it's sometimes going to be E for elasticity. And so here we have. Same thing can happen if you're going to bend something. So if you bend it, then we say this is your L naught, this is your delta L. And so it turns out being the same thing, that the force it takes to bend divided by the cross-sectional area is equal to the shear modulus. Shear modulus times the strain, delta L over L naught. Now, once again, different books do this differently. So your book actually uses G for shear modulus, because S is actually used for other stuff. S is used for entropy. Okay, so these two equations are identical. So the shear modulus is, in some books it's S, and in some books it's G. So you just have to kind of look at it in context. And so this is the idea of stress and strain. Now, if you were to graph stress and strain, okay, so you try to graph the strain, okay, so you apply stress to something. So you stress something and it strains. Then it turns out to be a fairly linear relationship. It's not always 45 degrees, but it's a fairly linear relationship. So you stress it and it strains. You release the stress and it goes back the way that it was. And so this is why we call this elasticity, is that you let go and it returns to the shape that it was, or the length it originally was, up to a point. Okay. There is a maximum strain here. The maximum strain, okay, is going to be the point of deformation. You stretch it, and if you go past that point, it does not go back the way it was. Or you bend something, it does not go back the way it was if you reach that. The maximum stress is called the yield strength. Now, once you reach that point, a little bit more stress tends to make massive strain, and it becomes nonlinear in a sense. And at some point, what happens is you reach the breaking point. And it actually breaks. The stress that creates the breaking point we call the ultimate strength. Okay, so these are our basic concepts of stress and strain. In your textbook on page 347 is a table of properties of materials, which gives you density, Young's modulus, ultimate strength, and yield strength for several sort of materials. And so that's something of interest to you. And again, if you're designing something, you do this. Now, I should also point out that for many objects, the ultimate strength in stretching we call the tensile strength, but the ultimate strength in bending is the shear strength. Okay. So that means some things are easier to break bending than they are stretching, or vice versa. You twist something, again, that's shear strength, and so you're changing it. So some things are different, and so concrete, for example, is an example of something that is exceedingly strong under compression, but it's very weak on bending. And so stone, similar sort of thing. And architecture, this is one of the problems they run into. So you put a heavy building, a roof on a building, and so in the ancient world, to support that, then if you just did that, then the weight of it here would tend to try to make it bend downwards, and it would break and collapse. So in the ancient world, the way they dealt with that was they would sometimes just have a lot of columns in here. So you see some ancient buildings that are just filled with column to support a heavy roof. Similar concept here, you know, for an overpass. You imagine near campus, you got Airport Freeway going over Precinct Line Road, and so you want to be able to support that. Okay, and so there's several different options here, and one of the options that you have is to put a lot of columns in there. Well, obviously that wouldn't work because you have to drive between them. So what else do you do? That's when the Romans in particular started the idea of an arch. Okay, and so you have an arch, and now you have another sort of thing. So as this pulls down, then obviously look what's happening here. As this pulls down, it has to change the shape. In order to go to that other shape, you have to compress it. Well, concrete and even stone is very strong under compression. It doesn't want to bend, but it will be exceedingly strong under the compression. So you're actually making it far stronger this way, because it won't it is strong under compression, and so it won't bend down like that, and you now have a stable structure right here. Now again, this was a problem they ran into that allowed them to make wide open spaces, but now you have forces on the walls that are pushing outwards on the walls, and well, now you're pushing outwards on the walls, and if they're concrete or stone walls, now you're shearing the walls. So one strategy they had in Roman buildings was to have extra thick walls. Okay, because remember, the stress is F over A, so if A is bigger, then you've solved the problem. Okay, problem with extra thick walls is it tends to make very the big walls make for very dark buildings here. So what they started doing in the Middle Ages was they would go ahead and build thin walls, but then what they would do is they would put buttresses outside the walls here that would support with the forces this way. Okay, and that would compensate for the forces that way on the walls. And so that strategy allowed for flying buttresses, which again allowed for vast open spaces inside of buildings. Okay, so back to the freeway overpass. So one strategy would be to make an arch here. Okay. So for a bridge, you can make an arch. In fact, there are bridges that are arches here. Well, that's not what they did for Airport Freeway. The other strategy would be that you support it and you make the road deck really, really thick. Okay, so you could make like a 4 foot thick, 4 foot deep road deck, and that would be strong. But that's not what they wanted to do. So they had another strategy, and the strategy is that you make this road deck here, and you have these beams here, and the road sits on top of that. Now, to make the beams strong, what they do is they embed in the beams steel, rebar. And so what happens is if it starts to stretch a little bit, that rebar turns out to be very strong and very elastic, and so it pulls back. And so it actually squeezes. If it tries to stretch a little bit, it will squeeze the concrete. Well, that's actually the direction the concrete is strongest. So that's how rebar actually works to strengthen concrete. Is that if you try to stretch the concrete with rebar in it, it actually squeezes it instead of stretching it. Or rather, I'm sorry, if you try to bend it, then it ends up squeezing the concrete, which is the direction the concrete is strongest.